Let's begin looking at solutions to some of the problems at the end of chapter 5. This is going to be a do while loop, or we're going to say I is equal to I minus k while I is less than the sum of j plus k. So all of these variables here are unsigned 32-bit variables. First thing that we're going to do is we're going to have a label to mark the top of our do while loop. Now we want to do the loop body, so we want to do the subtraction. So we're going to move the least significant word of k into W0. We're going to subtract that from the least significant word of I and stick the result back in the I. We're then going to move the most significant word of k into W0, and we're going to do a subtract or borrow of the most significant word of k from the most significant word of I and place the result back into I. We have implemented via these four instructions the loop body, which is this subtraction. At this point, we want to begin implementing the code that does this. Now, the first thing we need to do is implement this 32-bit addition. Our approach is going to be to use the register pair W3 W2 to hold this 32-bit sum. So first of all, we're going to move the least significant word of j into W0. We're going to add that to the most significant word of k and store the result in wreg, which is W0, and then move W0 to W2. So these three instructions right here have just computed the least significant word of this sum and placed it in the W2. We're then going to move the most significant word of j in the W0, add that to the most significant word of k and place the result in W0. Notice that we're doing an add with carry here, and then we're going to move W0 into W3, and we've just computed the most significant word of that sum and placed the result in W3. So at this point, the register pair W3 W2 has this 32-bit sum. At this point, we now need to do the comparison between this variable I and this sum. The sum is sitting in W3 W2. Our approach is going to be to take I and we're going to move that into the register pair W1 W0, and then we're going to do a 32-bit subtraction of these two values using compare instructions. So let's get started. We're going to first move the least significant word of I into W0. We'll then move the most significant word of I into W1. At this point, we now have I in this register pair, so now we need to do this comparison. So first we're going to compare the least significant words, W0 to W2. Then we're going to compare the most significant words, W1 to W3, and note that we're going to use a compare with borrow. After these two instructions have been executed, we've now done a subtraction of I minus the sum, and at that point we now can do the branch. Well, what branch do we need? If this comparison is true, if this condition is true, then we need to do a branch on the true condition back up to the top, and the true condition is a less than. So we're going to do a branch on less than unsigned up to the loop top. If this branch is not taken, it means that this condition is false, and we will exit the loop body. At that point, we have finished the solution to this problem. Problem 3 assigns k the bitwise OR of j and I, where all of these are 32-bit unsigned variables. So our approach would be, first of all, to do the least significant word bitwise OR. We'll do that by moving the least significant word of j in the W0. We'll then do the bitwise OR of the least significant word of I with the value in W0 and write that back to wreg. So now W0 is going to have the bitwise OR of the least significant word of I with j. We're now going to move that result back to the most significant, back to the least significant word of k. So now the k least significant word is equal to the bitwise OR of the least significant word of I with the least significant word of j. At that point, we're going to do the exact same operation, except we're now going to work on the most significant word. So this instruction sequence here is the same as that instruction sequence is now, except now we're doing the most significant word operations. At this point, we've completed a solution to this problem. A very common error in writing this code would be to leave off this wreg. If you did that, then you would be modifying the variable I, and the only variable that's modified in this case is k. So be careful when you're using these two operand instructions. Problem 7 is the same as problem 3, except that we're using 64-bit variables, unsigned 64-bit variables, instead of unsigned 32-bit variables. A 64-bit variable has 4 words, so all we're going to do is we're going to take the solution and extend it to 2 additional words. So first of all, this first 3 instruction sequence right here is going to perform the computation for the least significant word of I and J, writing at the K. This one right here is going to work on the next word, which we're going to call as word 1. This next 3 instruction sequence here is going to do word 2. Notice we're doing +4 to get to this word. And finally, this last sequence right here is going to work on the most significant word, and now our offset is +6 in order to actually get to the most significant word. At that point, we've finished this solution. Note that it's straightforward to extend 32-bit operations to 64-bit operations. It simply takes twice as many instructions. Problem 9 asks us to convert a decimal -42 to its 8-bit 2's complement representation. So our solution is as follows. In step 1, we're going to ignore this sign and simply take the magnitude 42 and convert it to hex, which is 2a. At that point, we're going to ask ourselves, is the sign negative? If it's negative, then we have one additional step. We need to subtract that magnitude from 0. So we're going to take 2a, subtract from 0. So let's do that. We're boring across a 0 here. It's going to leave that as an f. This is going to be a 16. 16 minus 10 is going to be 6. We're going to have 2 from 15 is going to be 13. So our final result here is going to be D6. So a -42 is going to be a D6. Note that if this was a positive 42, then when we converted the magnitude, we'd be done. A positive 42 is simply going to be a 2a. Problem 11 asks us to take the 16-bit hex value, which represents a signed decimal number in 2's complement form, and determine what the decimal value of this is. So the first thing that we're going to do is we're going to look at this number and ask ourselves, well, is the resulting decimal number positive or negative? By looking at the most significant bit, if it's 1, we know that the resulting decimal number is going to be negative. You can also look at this digit as f, and if it's greater than or equal to 8, then we know that the most significant bit's a 1. So the resulting sign of our decimal number is going to be negative. So we know the first part. We know that our decimal number, whatever it's going to be, is going to be negative. At this point, we need to determine this magnitude. Because this number was negative, in order to get the magnitude, we need to take this FBA3 value and subtract from 0. So let's do that. We're going to borrow from out here. So we're going to leave this as a F, F, F. This is going to be 16. 16 minus 3 is going to be 13. 15 minus 10 is going to be 5. 15 minus 11 is going to be 4. 15 minus 15 is going to be 0. So our magnitude is 045D. If we convert that to decimal, we get a magnitude of 1117. So we knew that our sign was negative. We've just determined our magnitude. For our final answer is hex FBA3, which is a 2's complement representation of a signed decimal number, is the value -1117. Problem 13 asks us to sign extend the 8-bit value hex 85 to 16 bits. So all we're going to do is we're going to copy whatever the most significant bit of this hex value is to the left for the additional 8 bits. We know that the most significant bit of this value is a 1 because this digit here is 8 or greater. So we simply fill in 1s for the extra 8 bits. In this case, that is in hex, that's filling in Fs. So a hex 85 in 16 bits is going to be an FF85. Problem 15 asks us to determine these flag settings for the hex subtraction 90 minus 80. So when we do the subtraction, we're going to get the value 06. Because this is a non-zero value, the 0 flag is going to be false, a 0. This number is positive because this digit here is less than 8, so the negative flag is 0. When we did a subtraction, we did not get a borrow from out here, so that meant the carry flag was left as a 1. Now let's determine the overflow flag, the value which happens to be 0 after the subtraction. This value here is a negative number because this digit is 8 or greater, so we have a negative P. and we're subtracting this value here, 8a, which is also a negative number. Let's just call it q. So we have minus p minus a negative q. That is the same thing as saying minus p plus q. If we take a negative number and we add it to a positive number, we cannot get overflow, so the overflow flag must be 0. Another way to determine the overflow flag, which takes a bit more work, is simply to convert these to their decimal equivalent. So a hex 90 is a negative 112, hex 8a is a negative 118. If we do the subtraction of minus 12 minus a minus 18, we're going to get a positive 6, and that positive 6 is the correct answer. So again, this tells us that overflow did not occur. Problem 17 asks us to determine these flag settings for the 8-bit hex subtraction 2a minus 81. This hex subtraction 2a minus 81 is going to produce the result A9. This 8-bit value is non-zero, so that means the 0 flag is false or 0. This number right here, the most significant bit is a 1 because this digit here is 8 or greater. So we have a negative result, so the negative flag is a 1. When we did subtraction, this digit right here is less than this digit, so that means that we're going to have a borrow from out here. When we have a borrow, it clears the carry flag, so our carry flag is 0. Let's now determine the overflow flag, which is going to be a 1. This number right here, 2a, is positive because the most significant bit is 0. So let's call that a positive p. This number right here, 81, is negative. This digit here is 8 or greater, indicating a negative number. So the operation is a positive p minus a negative q, which is the same thing as saying positive p plus a positive q. So we're adding two positive numbers. When we add two positive numbers, we should get a positive result. However, we got a negative result. That means that this is mathematically incorrect, which means that we had overflow. So our overflow flag is equal to a 1. Another way we can determine this is convert these values to their decimal equivalents. So a 2a is a positive 42, and 81 is a negative 127. When we do this, when we say a positive 42 minus a negative 127, we should get a positive 169. But this cannot fit in 8 bits. The largest number that we can fit in 8 bits is 127, so we're going to get an overflow. So which would mean that our overflow flag would be a 1. Problem 19 asks, what's the value of k, the final value of k in the following code segment? We have three variables, I, j, and k. They're all signed 8-bit variables. I is assigned a hex value A0. J is assigned a hex value 70, and this is going to compare I greater than J and assign that comparison to K. Recall that this comparison will return a 1 if the comparison is true and a 0 if the comparison is false. So the question is I greater than J or not? Well, I is a value A0. That is a negative number because its most significant bit is a 1. J is a value 70. That's a positive number because its most significant bit is a 0. A negative number is not greater than a positive number, so this comparison is going to be false. So the final value of k is going to be 0. In this problem, if we change this data declaration to an unsigned data declaration, so this would be a uint8, and ask the same question, then this comparison would return true, and k would be a value of 1, because for its unsigned, this number A0 is greater than this number 70. The magnitude of A0 is greater than the magnitude 70, so in that case, this comparison will return a true or a 1 value. Problem 21 asks us to take this signed variable I and assign it the value of A0 shifted to the right by 2, where we're assuming that the signed bit of the shift is preserved. So let's go ahead and do that. So we're going to write A0 out as in binary as this value right here. I'm going to start shifting it. We're going to assume the signed bit's preserved, so this signed bit's going to remain the same, and all these bits shift over to the right by 1 position. We're going to do the same thing again. The signed bit's preserved, shift all these bits over to the right by 1 position, and we're going to get this value here. The upper digit here is going to be E. This value here is going to be 8. So our final result here is going to be E8. When doing a shift, a quick way to do the shift is simply to determine which bits are going to be lost. In this case, since we're shifting 2 positions to the right, these bits right here are going to be lost. So I'm going to draw a box around the bits that are going to be kept, and then I'm going to fill in up here what my new bits would be. In this case, because our sign bit's preserved, our new bits are going to be a 1. At this point, I can determine my result here. These upper 4 bits are going to be a 1110, which is going to be an E. These lower 4 bits here are going to be a 1000, which is going to be an 8. Problem 23 is an if statement that compares K against J and executes this if body, which is a shift. Notice that these variables are all signed 16-bit variables. Let's go ahead and implement this in PIC24 semi-language. The first thing that we're going to do is we're going to do the comparison of K minus J. Because these are 16-bit variables, that's all we have to do is move J into W0 to compare that against K. So this is going to do K minus J. We now need to do this branch. Recall that we need the false branch here, so that if K is less than J, then we need to skip the if body. Because these are signed variables, we need to do an LT in the branch, the signed branch. So we're going to do branch on less than to our end F. At this point, we need to do this shift. Now, because this is a signed right shift, we want to preserve the sign bit. That's going to be our assumption for right shifts assigned variables. So we're going to do an arithmetic shift right of I. That's going to do a shift to the right by 1. Then we'll simply do it again and shift that to the right by 1. And at that point, we have finished the if body. What if these were unsigned variables instead of signed variables? How would this code change? So if these were U's here instead of I's, what we need to change in this code? The only thing we need to change in this code would replace the signed branch with the unsigned branch. So this would be LTU, and we would replace this arithmetic shift right with a logical shift right. That's all we'd have to do if these were unsigned variables instead of signed variables. Problem 25 asks us to write PIC24 code for this computation. Note that all of these variable names indicate that these are unsigned variables. So let's get started. The first thing that we're going to have to do is we want to take this 8-bit variable and we're going to 0 extend it to 16 bits. We need to do 0 extension because this is an unsigned variable. So we'll move Q to WREG, which is W0. Then we're going to 0 extend W0 into W1. So now W1 has our 16-bit 0 extended version of U8Q. At that point, we're going to move K into W0. We're going to add W0, which is K, to W1, which is our 16-bit value of Q. We're going to place the result in W0. At this point, we now have this sum, and the sum is sitting in W0. So now we want to shift this to the right by 2. This is an unsigned value, so we're going to do a logical shift right, W0 by 2 positions, place the result back into W0. At that point, W0 has this result here. So now all we need to do is bitwise AND that with this value A34D. So we'll move that literal value into W1. We'll do a bitwise AND with that with W0, which contains this. Place the result in W0. And now we'll simply move that to our I, which is U16I. At that point, we have finished. What if we take problem 25 and replace the unsigned types with signed types? What's going to happen at that point? Well, the first thing that's going to do is that when we extend this value from 8 bits to 16 bits, we're going to have to do a sign extension. So we'll replace the 0 extension here with a sign extension. Then once we do this sum and we want to do a shift to the right, since we assume that a shift to the right for signed data types preserves the sign bit, we're going to need to replace the logical shift right with an arithmetic shift right. So this logical shift right is changed to an arithmetic shift right. Other than that, the code remains unchanged. Problem 27 has us writing PIC24 code for this computation, which involves signed variables. Here's a 32-bit signed variable S. Here's an 8-bit signed variable Q. Note that this shift operation here is done before the subtraction. So let's get started. The first thing that we're going to do is we're going to take this 8-bit variable here and we're going to sign extend it to 16 bits. So we're going to move this 8-bit variable Q into WREG. We'll sign extend W0 into W0. So at this point, W0 will have the 16-bit sign extended value of Q. Now we need to take the 16-bit sign extended value of Q and extend that to 32 bits. Our approach is going to be to use the W1, W0 register pair to contain this 32-bit value. When doing this sign extension, W1 is going to end up with a 0. If this number right here is positive, it will end up with all ones, or 0x f quad f, if that number is negative. The sign extension is going to be done by these three instructions right here. We're first going to clear W1, which will be the correct value if the number is positive. We're then going to test the most significant bit of W0, bit 15, and skip, if clear, this next instruction. So if the number is positive, we're going to skip this next instruction because W1 will have the correct value of 0. However, if the number is negative, this next instruction will not be skipped, and we'll need to set W1 to all ones, giving it a value of quad f, which is the correct value if this number is negative. When we reach this instruction right here, W1, W0 will contain the 32-bit sign extended value of Q. We now need to take this 32-bit value Q and shift it to the right by 2. We're going to do that in two steps. We'll first shift it to the right by 1 and then shift it to the right by 1 again using these instruction sequences. Since this is a sign variable, we're going to want to preserve the sign bit. So we'll first do an arithmetic shift right W1 of W1. That's going to do a shift right on the most significant word. Then we're going to do a rotate right of carry W0 W0. That will do the least significant word shift. At that point, W1 W0 will contain Q shifted to the right by 1. We'll simply do this again to have W1 W0 contain Q shifted to the right by 2. Next thing we want to do is take this partial result here and subtract it from S. So the first thing that we're going to do is we're going to take that value that's in W1, W0 register pair and move it to the register pair W3, W2. And we're going to do that using this instruction here, move.double W0, W2. Recall that that's going to copy the value of W0 to W2, and then it's going to copy the value W1 to W3. At that point, we want to do the subtraction, but before we can do the subtraction, we need to get S into a register pair. So we'll move the least significant word of S into W0. We'll move the most significant word of S into W1, and now we're going to want to do the subtraction of W1, W0 minus W3, W2. So we'll first do the least significant word subtraction by saying W2 subtracted from W0, place it in the W0. That's the least significant word subtraction. Then we'll do the most significant word subtraction by doing a subtractive borrow of W3 from W1, place the result in W1. At that point, W1, W0 is going to contain this partial result. At this point, the only thing left is to do an inclusive OR of this constant with this partial result. So we're going to move the least significant word of this constant here into W2. We're going to move the most significant word of this constant into W3. Now at this point, we need to do an inclusive OR of this value with this value. So first of all, we're going to do the least significant word inclusive OR first. So W0 inclusive OR of W2. Write that result to W0, as that's the least significant word operation. We're now going to do the most significant word operation, or W1 with W3, write the result to W1. So now at this point, W1, W0 has our complete result, and the only thing that's left is to copy that, write that to memory to R. So we're going to write the least significant word, which is sitting in W0, to the least significant word of R, and then we're going to write the most significant word, which is sitting in W1, to the most significant word of R. At this point, we have solve this problem. Note that there are very many different ways to do this problem. We could have used many different register assignments as well as organize these operations in a different way.